Hi, hello, and welcome to our next 3D in 30 session. This is Velo 3D's LinkedIn Live and now YouTube Live channel. I'm excited to bring on today some great partners. I first met Justin and Augustine at REM at AMUG. This was probably 2.5 years ago now when I first joined with Velo 3D. And Augustine was giving a talk on the correlation between service finish and fatigue life. And I just found that fascinating to see that correlation. And that's a topic that we're going to dive into today, along with other topics like isotropic superfinishing, which is a term I believe REM coined. So if you've been keeping up with Metal AM, you might know this already, but in the surface finish field, metal 3D printers have improved drastically, and we'll cover a little bit about that. But we're still not yet printing at the surface finish of something that's been machined or finished. And in applications where you need that, you might need additional post-processing like what REM delivers. But which process should you use and why? And that's really the core of it. What are you trying to accomplish? Helping us to clear that up today will be experts on service finish, CEO Justin Michaud, and lead AM scientist Augustine Diaz. There's Justin. All right, Augustine. Welcome to the show. Thank you for joining me today. How are you guys doing today?
Very well. Thanks for having us.
Awesome. So, giving a little bit of background about yourselves, Justin, maybe you could kick it off. Talk a little back about your background, and then what was your first Metal AM experience?
Absolutely. So I'm, as Mike mentioned, CEO here at REM Surface Engineering. We are a third-generation family-owned company. We've been in the surface finishing industry for over 55 years. And additive manufacturing is sort of a passion of mine. I was first introduced to it about 10 years ago. And from there, we really had to build out some technology capabilities. Our background is in traditional machine components, so a lot of aerospace gearing and what have you. That was the link for us as to how we first got pulled in, because aerospace was certainly an early adopter in metal additive. And for us, it was a big change because precision gear. You're talking about taking off maybe 2/10,000ths per surface in our process to get to that really high isotropic superfinish, 2 to 4 microinch RA. Those first TIE 4 EBM parts we saw not quite that same level. You're talking about a much higher degree of roughness. So we knew we had to push ourselves a little bit, push our technology forward to be able to deal with that higher degree of roughness, higher degree of waviness. And that's what we've done over the last 10 years through a lot of work by Augustine and his team, and some nice government public-private collaborations on the SIBR side.
And was that your first exposure to Metal AM, was when you started seeing those original parts?
Absolutely. So I knew tacitly what 3D printing was, but hadn't really paid a whole lot of attention to, sort of widgets and things like that. So when we first started seeing some Pathfinder parts and fatigue bars come in, it was our first experience there, and we had to do some research. We had to understand, what was different about those surfaces and what was going to be required to treat them. And it took a little time, but that's become a big part of our business now.
Cool. Augustine, let's hear from you a little bit about your background.
Yeah, my background is actually I have a PhD in inorganic chemistry, and I did a postdoctoral experience at Texas A&M University on surface metrology, kind of surface science, and specialized on material sciences too in there. And I got hired at REM in 2014, and as soon as I arrived, I started seeing these parts coming from our customer base of additive manufacturing components. They were always asking, like, will you be able to do your REM magic, or what you have been doing for us all this time on these components? And always the answer was, well, that's actually pretty challenging. We're going to see what we can do about it. And we put like some time of it. I immediately identify, okay, this is something that I want to specialize into. There is a huge need for surface finishing of these components, and I just specialize in that specific type of components. Right now, I'm 100% focused on additive manufacturing. I am leading multiple SBIR engagement, or SBIR or SIBR efforts, as you want to call it, with NASA and the Air Force. The task is to try to understand what was happening at that point on those surfaces, why the surfaces were so different. That's when I immersed myself into the additive manufacturing field. That was my first experience. Actually, was with one of the notable Bello customer, Bob Markley. That time he was in Third Dimension, come with this really interesting project. Also, back in the days called Ad Aero, now is a part of ATI technology. They also were coming with this really interesting type of components, and we have those initial conversations like, okay, what's going on? And they actually help us to understand a lot better the technology and why the surfaces were so different. And back in the days, there were not that much research out there talking about this kind of stuff. And we were kind of pioneers, start talking about, okay, this is what happened on the surface, this is happening on the subsurface. Now you go to a conference and they talk mostly 90% of what we've been saying since 2015. So it's really interesting. I'm really proud of that achievement, that we were one of the pioneers identifying those problems and tackling them.
And did you start as lead AM scientist? I mean, that's been your goal from day one in 2014?
No, actually, I started as a senior chemist. Our process is chemical based, so we was working more into the formulations and optimization of surfaces to improve certain properties of the components. So basically, always what we were looking is to improve corrosion resistance of the component, or improve fatigue life, or get that nice RA values of those surface texture features at the surface. And that's basically how we started. But I think within 6 months, I was already 100% into additive manufacturing, and I become lead AM scientist and start getting my own research on additive 2015, I would say.
And you kind of mentioned a couple things there, like fatigue, corrosion resistance. Is that what people are mainly looking to get out of a process like this?
Well, that depends. People have different kind of application to their components, but most of the interest in additive, I will say right now, is in fatigue. Right, everybody's trying to get this really complex type of component that can have these great properties that you should have from traditional type of manufacturing, right? So what I like to do is that I can produce smooth, pretty surfaces. But there's a lot of technologies out there that can achieve that. I would like to add another level of value to that component. You print the component, your component have that level of complexity, but also I would like to have that extra value of performance, right? And I think that it was the magic word that we start looking into and really trying to achieve. And that's what we achieve quite fast, right? Improving surfaces to improve mechanical properties. And that was like basically a huge need in the field. Maybe we got lucky, but it's kind of makes sense, right? You want to add values, make surface prettier. Yeah, that's a challenging task. Now, making it better, that's an even more difficult task. And that's why we have all these resources just focus into this type of research and trying to make it happen.
And so, Justin, I kind of want to shift to you a little bit. We've heard some of the value that REM is creating. What do you see as a way for REM to differentiate in the market? What's your driving force there?
Yeah, so I think we're kind of unique in that we're really focused on, like kind of like what Augustine's describing, being solution providers, right? Where we have our greatest successes, where we're solving problems for a customer and adding that value. So, if you look at the surface finishing market, there's a lot of folks out there that sell equipment. There's a lot of folks out there that do sort of just outsource job shop processing and what have you. And they tend to, as a result, shift you in one of those directions and limit some of your options. That's not really our business model. We're happy to do either of those things and really support customers however best fits their business model. So, we're not often the cheapest solution. Sometimes we are, but we're typically the highest quality solution. So that's really where we separate ourselves from other options that are out there.
But,
and I think we have... Oh, go ahead.
Yeah, a little bit of that is like we are not the cheaper solution because at this moment we really understand the complexity of what additive manufacturing is. I cannot come with mostly generic type of approaches to really complex components. So the initial part I will think is the expensive one. Now when we figure that out and everything is kind of validated and locked in, then become, in my opinion, highly affordable, especially because what we produce is a mass finishing option, right? So volumes make it a lot more affordable.
Nice. And just for anyone who's watching today, I understand we have some people viewing in. We are talking live to REM. So if you have any questions on post-processing of metal AM parts, go ahead and drop a comment in and give us a question. We'll answer it live. So yeah, looking forward to hearing from you. Yeah. In the work up to this, we had a couple calls, and you mentioned a term that was new to me. It was smearing of the metal. When I thought that was kind of interesting. So, what would you define as a smearing process, non-smearing? Which one would REM fall into? If you could maybe talk about that a little bit. Maybe Justin, if you want to kick that off.
Sure. I can open that up there. So when we talk about additive manufacturing and specifically laser powder bed fusion, or really any of the powder bed fusion processes, there's roughness that you see on the surface, and then there's often some subsurface porosity that's present, just based upon the build parameters and what have you. A process like REMS it's a non-smearing process, right? We've got sort of two angles of attack. We've got a pure chemical process that's really optimized to planarize the surface. Then we have our chemical mechanical polishing, which is built on our traditional ISF process that we use for the precision gear applications and whatnot. And it's great at getting rid of more of that waviness and getting that really low roughness surface. But neither one of those are high energy processes. So if there's any sort of subsurface porosity, we're going to expose it, right? We can't hide that. There's other processes out there that are sort of higher mechanical energy and whatnot, where you can actually sort of fold metal over the top of that and hide those. Hand polishing is a good example of that. It's very good at that, right? And for some applications, that's necessary because you need that decorative high gloss, and it's otherwise not possible because maybe it's binder jet and you have isotropic porosity without the entire component. So on the laser powder bed side, that's a different ball game. That you need to deal with it. You need to address it. Not every application, it's not important for every single one, but for ones where, specifically like fatigue oriented ones, that's going to be a fatigue debit. So if you can't remove that and remediate that, it's going to have an impact. And so derivatively, that's kind of one of the values of our process is that we can work as a little bit of the quality check, as well as becoming that final step in the manufacturing process to get you the surface you need for whatever performance you're looking for.
So it's a little counterintuitive, but it sounds like while you focus on surface finish, you're actually getting a good view into the subsurface in some ways, where the subsurface becomes even more important. So I guess I'm kind of wondering from that point of view, how does metal AM compare to other processes like, let's say, casting or something like that?
Sure. So casting and MIM and binder jet, I'd say have a lot of really strong similarities. You're gonna have scattered porosity throughout the entirety of the part. You're gonna have varying levels of density. If you shift that over to laser powder bed fusion, it's gonna differ a decent amount now. So laser powder bed will typically have a little bit of a higher starting roughness than say a cast component, but it's gonna have a higher density. But that density, the point where it's gonna have more porosity is gonna be in that contour layer, typically, right? So you'll have, let's say, 99.9% dense, but that 0.1%, it's probably all located in that first 100 to 200 microns of material depth, 4 to 8 thousandths into the component. So if you can remediate that, now you can have a really high performing component that can achieve some of the things that we're looking to do in terms of replace forged parts and typically machine components.
And Augustine, what are you seeing when you work on these parts? What are you kind of revealing?
Yeah, so basically what I told the customer is okay, this is not just a surface finishing operation, you're also going to have like a quality check on them. So if something went wrong through your printing, especially if you have something wrong with your contour type of parameters and you include any type of porosity in there, or you have lack of fusion, I'm going to be able to tell relatively quick, right? Because the process is really gentle. It's basically chemistry is what is doing the force, right? Is what is removing the metal, and that's just going to be given by the energy of the surface, right? And those are really weak forces. Sorry. So when you start removing that metal, the first layer that you remove chemically is going to be that accumulated powder that is at the interface between the component and the powder bed. So you remove all that partially melt, partially sinter, and then you get deep into that contour. So if your contour parameters have any type of problem, we're going to be able to see it. And also, if you remove enough metal and you're capable of getting to that interface between contour and hatching, I'm also going to be able, if you have perfect alignment on that turn of the hatching versus the contour. So those are basically where all the problems are kind of associated. What we do is we play it safe, right? We talk with the customers like, hey, if you can get a print in which you can overgrow by a certain amount of material, and that is allowed due to the geometry of the component, let's do it that way. that if you go that direction, you kind of play it extremely safe. You remediate most of the problem of the component, and that's how you get that increase on fatigue performance, because basically you eliminate all the stress racers at the surface.
So we do have a question, and it kind of relates to what you're talking about here with removing the metal. How much material are you looking to remove?
That's an excellent question. It will depend on what you're looking for. I can produce smooth surface where the industry is always looking for this RA value. So we can achieve RA values in the single digits within 17 microns sometimes. Sometimes you need to go a lot more. Everything will depend of the print quality and how smooth your parameter were, and several variables. I recommend to play it safe to remove at least 250 microns. That's 10 taus. Some people get scared of that. At the beginning, when we started doing that in 2015, I had a lot of pushback from customer, like amazing pushback. Nowadays, it's kind of implicit. All of them come asking, hey, remove 20, remove 30. Why? Because they have done their do research and they have all these data of high resolution X-ray CT scan, and they figure out that most of that problems are in the near surface down to that. So it gave them like a really high level of confidence of that component if they remove that much of material.
I think we have
the classic answer, Mike, is of it depends, right? I mean, so
yeah, of course.
You got to back it up a little bit and say, well, what printing processor are you utilizing, right? Typically, laser powder bed, you're not taking as much material off as if it was, say, electron beam melting, right? You're typically taking a lot more material from EBM. I mean, we know Ti-64 EBM pretty well. We know Ti-64 LPBF because it's a lot of the stuff that tends to get sent our way. EBM, it's pretty common to take 20,000, 500 microns, something in that range. An LPBF, as Augustine was saying, 250 is a conservative number. We've seen great prints where less than 100 microns, and you're getting to better than machine quality surfaces. But it really depends. Alloys impact that. What thermal processes you do impact that. There's a lot of things that get in there. They're really what we would encourage folks is the right way to approach that is from a collaborative perspective, and that we should work with some parts, and we should do a study where we chart roughness change and surface texture change versus material removal, and it's going to tell you a lot more at that point in time, and you can make better decisions on your material offsets.
Yeah, I wanted to add another point. Sometimes you also want to do this surface material removal based on printing limitations. So let's say you want to have a feature in your component that is going to be a wall with certain amount of thickness, and you have the limitation of the printer, how thin you can print. So there is not a problem because you print with high level of confidence, and then we chemically remove that extra amount of material. That's something that we're actively doing with NASA. And it's turned out to be like really, really good, because now those limitation of wall thickness doesn't exist anymore. And we have control of surface material removal, and how uniform it is quite uniform. And then you can achieve those targets.
And I actually think we've got a nice image of an impeller that was finished. Augustine, maybe you could walk us through here a couple questions. I mean, A is, in the theme of how much are you moving, do you remember how much was removed on this part?
I think for this one, we removed around 150 microns, if I remember correctly. This is a Velo 3D component. It was printed without support structures, which is really nice for an impeller like this. They have a lot of internal features, and we were able to flush the chemistry uniformly through those internal cavities and get rid of all those macro defects at the surface. Produce a really cool and beautiful surface.
Nice. Well,
that was a Ti-64. It was a Ti-64 component, by the way, titanium 6.4.
And there are a couple questions, and I want to get to those. So, how do you deal with defects like porosity when you uncover that?
Yeah, I mean, simply put, from our perspective, yeah, exactly. We're a purely subtractive process. We're not adding anything to that. It kind of goes back to the comment before that, we're not smearing metal. So if it's present, the only option you have is to go beyond it. You've got to continue removing material till you get beyond that zone of porosity concentration, and then you can fully remediate it. If you can't fully remediate it, a unique thing about our process, because it's chemical and chemical mechanical, is at a minimum, we can alter the shape of that porosity, right? Those sharp V notches and what have you, those are those stress concentration points. They're also bad for corrosion. If we can change the angle of those and radius those and make it at least a more gently rolling type of valley rather than a sharp valley, that can also be of a benefit. But that's your best case scenario is obviously to get rid of it entirely. Sometimes there are geometric limitations and what have you that mean you have to make some compromises.
Okay. There's another question. Somebody just wants clarification here, and Kyle's asking, you're getting a surface finish of less than 100 RA after print, or you're machining after the chemical removing, maybe what's the order of process there? Do you machine? Do you need to do that afterward?
So that one was as print. We chemically polish that component for 150 microns, and that's basically what is the final product. Sometimes and when you say 100 RA, I want to assume that you're talking about micro inches, not microns. So yeah, you can achieve with chemical polishing RA values within those 60 micro inches. If you want to go an extra step, we do the mechanical polishing. In that stages, you can produce RAs of 4 micro inches or less. We're talking about 0.1 microns of those ones. So in that specific feature on there, I think we did the chemical mechanical polishing on the top of it to get that perfectly flat surface. I recommend for improvement of fatigue to go the 2 ways. We remediate all the macro defects, chemical polishing, and then we do a chemical mechanical polishing operation to be sure that everything is gone, that you get rid of all those extra defects of the surface, and that's going to produce the best possible surface. Usually RAs of those are below 0.1 micron or 4 micro inches.
Yeah, he does confirm it was micro inch.
Yeah.
So there's another question here. Do you need to predict the removed amount of material? And since it changes the geometry, how should a designer compensate for that?
Yeah, that's an excellent question, and that's why say that probably our process is like in the expensive side of the equation. It is, and I defer. It's like, no, we need to understand how you're printing. Each person have their own printing parameters set up. They have a lot of variation between equipment. There is a lot of variation in powder that they use, how many times they recycle that powder. All of these factors are going to have an effect on the outcome of that component. So what we need to do first is, as Justin said, we can do an experiment of surface material removal versus surface planarization. And that way, basically, we see that those graphs, like the one that I have right here, that goes down. Sometimes you get that stuff going down, then goes up again, and then goes down. What happened there is that, hey, you start planarizing perfect, and then you get all the defects in the contour layer, probably space between contour and hatching was not optimized, then got higher because you have porosity, and then you go to the hatching bulk of the part, and then you goes down again really quick. So it's going to depends a lot on the printer that you're using and how you're treating your powder and the angle in which you build, and then you have an instrument superstructure. So there is not an easy answer, but that's what we specialize in. We're going to find a solution, and we're going to tell you exactly what it is. And as long as you don't change anything, it stayed really well standardized like that. If you start recycling the powder like an extra couple of cycles, or you change the part alignment into the powder bed, and now you have like more of extra surface that is overhanging and stuff like that, that's going to get more complicated. But as long as you locked in your process, we can lock in our process when we did that initial testings.
So there are some people who are curious about learning more about the process. Is there a place that they can go to learn more or see videos on the process?
Yeah, absolutely. So we've got a decent amount of information on our website. We can pretty easy to find. We can throw that up in the chat after this, where we talk about it. I mean, at a high level, at a basic level, there's 2 primary technologies that you heard Augustine reference. There's chemical polishing, which is going to be a pure chemical dissolution process. It's extremely flexible. It's a bit more refined than your typical chemical milling, which is more about bulk material removal. We've designed our chemicals and our processing parameters to really flatten that surface and look to remediate it. We can eliminate all the granular roughness from powder bed, and we can look to remediate as much of the waviness from that laser scan strategy as possible, but it has some limitations there. The chemical mechanical polishing process, now you're switching into a mass finishing environment, but rather than utilizing abrasive to just scour away the surface, we're using some chemical activation in addition to non-abrasive media typically to planarize and flatten that surface further. So that's why you can use those processes individually. You can use them in combination. Sometimes geometries will limit that. I see there's a couple of questions about channel length and things like that. I mean, we're doing the cooling channels on regeneratively cooled rocket nozzles. Talking about 1 millimeter type of diameters, 15, 16-inch long runs, 300, 400 millimeter long runs. So the chemical polishing is extremely flexible. The chemical mechanical, when you start getting below, 10 millimeter type channel sizes and what have you, start having some limitations. You can do it still, but at a certain point, there's diminishing returns and you would be limited to just the chemical polishing. But we've got some pretty good experience with, complex waveguide applications, 15-inch long type of waveguides that have some serpentine bends, and we can still get some pretty solid RAs in there. You're probably not talking about single digits anymore, but you're still talking about something in that, 1 to 2 micron, 40 to 80 micro-inch machine type surface.
Yeah.
About the X-ray.
Yeah. Oh, go ahead, Augustine.
Yeah, about the extra information also, I am really active on the peer review type of articles. So I an active author and actually reviewer of those articles. So if you go to my Google Scholar webpage, you can find all the peer reviews that we have. I love to put the process to the test, because if there's something going wrong on it, I can fix it. And that's exactly how we have getting all this funding from NASA, because we publish a paper collaboration with the Aerospace Corporation in which we have a process for titanium that was chemical, and then we use abrasive for the inconels, and the inconels fail badly on fatigue, so no improvement whatsoever versus the as-built. It was like, wow, interesting. And based on that, we were able to get an SBIR from NASA, and now we have a process for Inconel 625 that is outperforming everything, so it's really good. So that's how I develop my research, and I put it to the peer review, and I put it to the test every single time because I want to make it better and better and better.
And is there a resource that someone can go and learn more about that? Can we get a link to them maybe?
Yeah, I can put a link in the bottom. My Scholar, Scholar Google, Agustin Diaz, and probably you're going to have the latest 5 years of publication is going to be especially on this.
Yeah, most of those are on our website as well. We try to have a pretty robust resource section on the website, so you can fill out the little contact form, and then you have access to all that stuff. So no, we try and share as much of the data as possible, and help advance the industry.
And there were some questions. Oh, go ahead.
And LinkedIn too.
LinkedIn.
Yeah.
There were some questions about the challenging geometries, and I think you got into that. And Augustine, I think you started to get into a little bit of the metals. I mean, what are the challenges just in general, geometries or alloys or heat treatments? I mean, what do you see out there that makes it complicated?
Well, it's complicated, but it's complicated good, right? Because it's that additive manufacturing gives you that extra degrees of freedom to have almost free form. It's not 100% free form, but you can get away with a lot of geometries that are impossible to build with other type of technology. Now, that type of complexity is awesome for the components for the application, but usually it's a nightmare for the surface finisher. So if you go with traditional surface finishing type of application that are based on abrasive action or like shot peening and that kind of stuff, it gets really challenging. And that's when the level of complexity gets up there. In our case, we go with the use of chemicals that are usually really gentle to geometry and complexity, as long as you can access all the surfaces at the same time. There's a lot of engineer type of solution that we have in-house to achieve those really complex type of components. But also because the process is chemical, is going to be affected by the type of heat treatment that the components have. And this is really important. In additive manufacturing, and heat treatment need to always take into account. You print a component, and most of the time it's not coming from an EVM type of machine. You're going to need to do a stress relief, right? So that's your initial heat treatment. Sometimes you need to do solution aging. Sometimes you should have heat the component to remediate most of the porosity that exists in that part. And all of that is going to be changing the chemistry of the alloy by itself. And that's something that we need to take into consideration, which type of heat treatment you're doing, because that's going to affect the surface material removal rates that we're going to see in our process. The chemistry is kind of basically the same for each alloy, but it's different between them. So Ti64 have their own chemistry that we develop. The Inconel 718 have their own chemistry. GR cups have their own chemistry. So they vary within these families of chemicals, but how they interact with that material is going to change based on the chemical composition of the component that you have. That changes with heat treatments.
And do you see any interaction between the chemicals and having an effect on fatigue other than just surface, but a chemical side? There's a
Yeah,
question in
there's
here
yeah,
on that.
yeah, there is always like that concern in the industry that you use chemicals on metals and you are risking to have hydrogen embrittlement, for example, or you have intergranular attack, intergranular oxidation. And that is like really well established concern because those are real. So when we develop the formulation and where we're doing our research, we're always looking to avoid those. So those are the commandment that we have. First of all, no hydrogen embrittlement. So you need to use hydrogen scavenger in your formulation if there is, for any reason, you suspect that hydrogen is going to form in that reaction. You should have important monitoring system to see that you are not going into the intergranular attack, that you are not going into intergranular oxidation. All of those, you put it to the test. So you do your formulation and then you test it and be sure that that doesn't exist there. So we are really actively looking into those. And that's when you have that detrimental effect on fatigue and tensile.
There was a question on, can you guys scale your machine? What are the limitations on size?
Sure, I can speak to that a little bit. So there's not too many limitations, although as you say that, and then I can tell you that NASA's pushing us in this area right now. So coming from our traditional side of the game, where we do a lot of stuff, we do a lot of work in, like, let's say, the wind turbine gearbox industry, right? So we've done parts that are 2 meters in diameter, annuluses, 10,000 pounds. Like the process can fit those things, no problem. NASA is currently, we actually have just won a phase 2 extended award with NASA, whereby we're going to be scaling our process capabilities to be able to do a roughly 6 foot by 6 foot rocket nozzle. It's about a 65% RS-25 nozzle. We got to prove that concept out and show that it scales. Everything we've done so far suggests that it has, and that it will. And then once we do that, then they're going to do a full size RS-25, so 10 foot by 12 foot. So there's no limits to scaling. At a certain point, obviously, as you're adding weight and size, I mean, your CapEx grows up from your equipment perspective. But as long as there's a need, as long as there's a value, the nature of our technology, utilizing the chemistry, so we're not overly reliant upon high levels of energy and force, you can scale pretty effectively.
Well, we got a lot of questions here. Let me jump on one for Velo. Post machining is not a part of the Velo 3D product. The Velo 3D product is an advanced metal 3D printer capable of making some amazing things. But if you want to get that, like what we're talking about, these kind of surface finishes, reaching out to post-processing partner like REM is a way to do that. So definitely not a part, but a partner. So we could say that much. So I do want to be cognizant of time. I'm going to deal with maybe one or two more questions, and then we are a little bit over right now. But are you guys okay to stay for one or two more?
Absolutely.
Absolutely.
So there's a question: does the flow of the media around the part have an effect on the uniformity of the finishing result?
Yes, I'll jump with that one, and August, you can maybe add some details. So yes, it does. But when you compare it to like a traditional tumbling operation, it's a lot less impactful. So I'll go to our traditional world of finishing for gears for a moment. One of the reasons we're so successful in gears is we're able to maintain flake profile tolerances to like micron levels. And it's because of that chemical activation we're doing of the surface on the chemical mechanical process, or the ISF process in that world. Because we're doing that, we're lowering the required force you need to take material off that surface. And that means that you don't need, you're not going to have as much bias, from raised areas versus recessed areas. You're going to have some at a certain point. And as you extend material removal to higher amounts, that can become more impactful. But there's a lot of different ways of addressing that. And typically the tolerances that we're going to maintain are going to be tighter than the tolerances that you're seeing for most of the printers, even the really advanced ones like Velos. So we're typically not going to be your big challenge right there. We need to talk about material offsets, obviously, based upon what type of roughness you're looking for. But as long as we can accommodate that, we can do some pretty good things there.
And the last one, is there any technology available capable of printing in a high vacuum chamber? Must be used in space. I can say from the 3D printing side, our technology is probably not a good mix for that. Laser powder bed fusion has a powder bed of metal, 50 micron kind of granules of metal. I don't think you want that in a vacuum. There might be somebody out there who's working on it. I understand made in space is definitely an initiative. But I'm curious, would your process be usable in space?
So the chemical polishing, I'd say for sure, right? Because we do a lot of chemical polishing applications where we're actively pumping through or around a component because it just aids with the the uniformity of delivery of the chemistry. So something like that, sure. I think the vibratory dynamic might be challenging. You could probably get away with maybe doing some centrifugal type finishing and centrifugal disc machines and what have you, where it's effectively simulating some gravity via motion, but it would add a new layer of complexity. It's not something we've done.
Yeah, I don't think you want that floating around in the capsule. Well, I mean, we're definitely a little bit over. Thank you for staying somewhat extra. I do want to kind of close out with, if you have any closing thoughts, and then what's the best way for people to get in touch with you? So maybe Justin, if you could kick that off for us, and then we'll close out.
Sure. So obviously LinkedIn. Obviously, and I are both very active there, sharing things. Of course, our emails, I think will be shared here at the back end of this. We're happy for folks to contact us that way. Our website, we try and add content. We try and add resources fairly regularly and discuss our processes. Again, we're not a black box. We're happy to be open about how we're doing things. And then, the show. So Augustine and I have some talks coming up at Rapid. Definitely come by, see us there. We have some talks at ICANN, ASTM later in November. Hopefully everything keeps going. And we're very open and available.
Nice. Augustine?
Yeah, please, if you're going to be needing, think about additive manufacturing as a really complex type of process. Sometimes you are not going to need a surface finishing operation. But if you do need a surface finishing operation, please keep in mind that there's going to be some materials that needs to be sacrificed in the process. So when you do those designs, take into account that probably are going to need to remove 100, 200, 300 microns out of that surface. And also how it's going to be finished and the RA value that you're looking for. That's a big one. The RA value that people are asking for. We didn't have time to talk about that in this one, but they're going to be in the news in the next one, like part 2. We're going to talk about that one.
All right. And since you said part 2, that's a good advertisement. So please follow Velo3D to find out when we're going to launch that part 2. 3D and 30 is our LinkedIn live and YouTube live channel. We do these about every 2 weeks. So stay tuned. Follow Velo3D to find out more about the next one. And please reach out and follow REM. It sounds like you guys are already active on LinkedIn. I can tell from the questions. It sounds like people are already following you. So that's an awesome sign. But if you're not, please do. These guys are amazing experts and a great resource for you. So thanks, everyone, for joining us today. And thank you, Justin and Augustine, for joining us on the show.
Thank you, Mike.
Thank you. Have a good one.